Okay, thank you for having me. My name is Deep Datta, and I am the Community Product Manager at JFrog. And I'm going to be talking a little bit about the security considerations that were put into Go modules. So let's go. Okay, so you probably know that Go has gone through a few different methods of dependency management. We started with Glide, GoPath, DEP, and of course dealing with some issues with vendoring. But as Go evolved, the language leaders basically realized that none of these were the perfect fit. So with Go 1.11, they released something called Go modules. And a Go module is basically a collection of packages stored in a file tree with a go.mod file at its root. And with Go 1.13, which happened last year, Go modules became the standard. Something that was introduced with Go 1.13, which is pretty cool, was some security standards that were brought in to help make sure that data is authenticated. So a file was introduced called Go.SUM file that has a list of hashes that are used as checksums. These checksums are authenticated against a database called GO.SUM and I'm going to be explaining a little bit more about how that works. So to start, I'm sure you've all seen this. This is your Go.SUM file, and this has a list of SHA-256 base 64 hashes. These hashes are used to check and authenticate that a block of digital data hasn't changed during its transmission or storage. So these hashes are checksums. They're used to verify that the original data is the same, that it hasn't been tampered with, and that it's still intact when it was being transmitted. And with Go, this helps make sure that the same dependencies that were originally committed to the module the first time it was built hasn't changed when a user goes to import that module at a later time. So I'm going to touch more briefly on some specific concepts. So the way a SHA hash works, Go uses it's a SHA-256 base 64 hash. And this works by taking a piece of data as an input and then putting it through the algorithm, through a system of mathematical equations that will output a set of bits that result in a 43-character string. And no matter what the input is, whether it's a text file, a graphic image, a video, what comes out the other side is always that 43 characters. And what's really cool is a single character difference in the underlying file that you input will produce a very different output hash. This is really important because if I am, let's say I hand you this 43 character hash, and then later down the line you import a module, as long as that module, hash matches the one I handed you in the beginning, you know that the data has stayed intact through the transmission. All right, so one more concept I want to talk about before going back to Go modules is the merkle-tree. So Go's checksum database uses a merkle-tree structure, and this is something that also is used in blockchain. So at its core, a merkle-tree is basically a list of items representing the data that should be verified. Each of these items is inserted in the bottom right there in the leaf node, and then it is hashed, and then it is hashed again all the way up the tree. So each hash is combined and hashed all the way up to the root node at the top. And one advantage of this is that if somebody needs to go verify the data in the log, they really just need to verify the root node. It makes it much faster to verify any specific piece of content. And the other really cool about a merkle-tree structure is that if a single record is changed, then the list of hashes changes as well all the way up the branch, and they no longer line up at the top. This makes it really easy to understand if anything was changed. Basically, any misbehavior in the data is immediately detectable. So if I have two Go modules, they both have their own list of SHA-256 hashes, and they're both committed to the GO.SUM DB, that's fine. But if I have one module and somebody clones my module and makes any small piece of data change, a different set of hashes will be in the GO.SUM file, and this module 1 that someone cloned can no longer be committed to the database. It'll it'll send a checksum mismatch error. And this means that somebody importing my module later knows that they're getting the right module. So let's say that you create a module for the first time and you save it and you commit it to the database, but then you realize you made a mistake. So in this example, I've imported a package called text/template, which is going to open up my app to cross-site scripting issues. But I've already committed this and saved it as mod1. So what do? Well, I can, of course, fix the module, but then I actually have to save it with a different version. So using the right semantic import versioning, I'm going to save my module 1 as a v2. That way, now when I am committing it back to the database, Google knows that these are different versions of the same module, and this means that the checksums will be unique, they'll line up, and they'll be committed. So this ensures that the data is intact, it hasn't been tampered with, but it does not make sure that the actual code itself is safe. So if somebody goes and finds my original mod 1 and imports it later, it's authenticated. They're going to get that module 1 that has that vulnerability in it. So how do we protect against this in your dependencies? We at GoCenter have built basically a security scanning right into the UI. So GoCenter is a module mirror. It's a large GoProxy with over 700,000 imported Go modules, always available. And we've provided free security scanning on the security tab. So you can actually go and see every single module and every single version, and we'll provide you the vulnerability information. It also has a versions tab that shows you which versions of your module are safe to use and which ones are not. So that's my talk. Thank you so much for having me. If you have any questions, my Twitter is DeepDattaX. I look forward to hearing from you. Thank you.